Hey, welcome to high school chemistry. My name is Rex. Today we're going to study atoms, molecules, formulae, and equations. First, we're going to define atoms, molecules, and ions. But before we define them, let's go back to 400 BCE, when Leucippus and Democritus were philosophically talking about atoms. They said that all matter was made up of small, indivisible particles called atoms. Atoms come from the Greek word atomos, which means indivisible or uncuttable. So thereby, an atom, which is the smallest unit of matter, cannot be divided into any smaller units. And now, from this thing I just said, an atom is the smallest unit of an element, which can take place in a chemical reaction. You can also say that an atom is the smallest particle of an element that can exist by itself and still retain the chemical properties of that element. Atoms don't just exist by themselves. Atoms combine with other atoms to form molecules. So a molecule can either be monoatomic, diatomic, or polyatomic. A monoatomic molecule is an atom that exists by itself. It doesn't bond with any atoms. And a good example are the noble gases. Examples like helium, neon, krypton, xenon, and argon are some examples of monoatomic molecules because they can exist as themselves. They are not molecules, they are atoms, but they are monoatomic atoms, which means they can exist independently by themselves. Then there are diatomic molecules. Diatomic molecules are molecules that are made of two of the same atoms or two of different atoms. An example is the hydrogen gas, which is a molecule that consists of two hydrogen atoms. There's the oxygen gas, which consists of two oxygen atoms, and there's even hydrochloric acid. Hydrochloric acid is made from two atoms, which is hydrogen and chlorine. So chlorine is one element, and there's hydrogen, which is also another element, or another atom, which makes up the molecule. And lastly, what about polyatomic molecules? Polyatomic molecules are molecules that contain three or more atoms. An example is ozone. Ozone is three oxygen atoms. And three oxygen atoms that make up a molecule can also be called a triatomic molecule because it contains three atoms in its molecule. Another example is H2SO4. H2SO4 is two hydrogen atoms, one sulfur atom, and four oxygen atoms. Let me write that down. So this is H2SO4. Here you can see that there's H2, which is two hydrogen atoms. So there's two hydrogen atoms. And then there's one sulfur atom, and then there's four oxygen atoms. Alright, so let me clean that off. There's one thing I want to clarify though. Sometimes students can get elements confused with atoms because what is an element? An element is the simplest unit of matter which cannot be divided into any smaller units by an ordinary chemical reaction. This sounds similar to an atom, which is the smallest unit of an element that can exist by itself but still retain the chemical properties of an element. So what is the difference between an element and an atom? Well, here's an example. If I brought a gold bar, we all know that gold is an element. If you didn't know, now you know. So gold is an element, but a gold bar is not one atom of gold. An element can be one element of gold. Like if I brought a gold bar, that can be one element of gold. But if I brought a gold bar, that isn't one atom of gold because there are like million, trillion, septillion atoms inside that gold bar. So an element is like a substance consisting of the same type of atoms because atoms will still remain the smallest unit of matter. So from what I explained about molecules, the polyatomic, monoatomic, and diatomic molecules, what is a molecule? A molecule is the simplest particle of a substance that can exist by itself normally, but still retain the chemical properties of that substance. And now we're going to talk about ions. Normally, atoms are neutral. It means atoms have no charge. But there are sometimes that atoms can either have a positive charge or a negative charge. If an atom has a charge at all, whether it's positive or negative, then that atom is said to be an ion. A positively charged atom is a cation, and a negatively charged atom, is an anion. So this is the spelling of cation, and then this is the spelling of anion. You got that? All right, let's move on. So now that we've defined atoms, molecules, and ions, because remember I said ions are atoms that have a charge, and I'm going to explain why atoms sometimes don't have a charge. But anyway, let's move forward. Let me tell you a story. In the year 1808, an English chemist called John Dalton proposed his atomic theory on the way atoms work. He was studying atoms, and then he came up with 5 solid theories. These theories were widely accepted by the scientific community, but at some point in the late 20th century, people like Ernest Rutherford, Albert Einstein, Max Planck, and even other brainy scientists came along and began to modify his theory because his theory was flaky and there were some loopholes in his theory. But you will notice that only one of his theories will remain. So let me list them out. Number 1, John Dalton said that an atom is the smallest indivisible particle of matter. It means it's the smallest building block of matter. And this means it cannot be divided into any smaller units. That was his first theory. His second theory says that atoms can neither be created nor destroyed. Okay? Then his third theory says that atoms of the same element are identical in every aspect, and they differ from other elements. Number 4, he said that atoms combine, and when they combine, they do so in simple ratios. And lastly, number 5, he said that when there's a chemical reaction, whether it's an ordinary chemical reaction, or nuclear chemical reaction, or any other chemical reaction, it always involves the separation or combination of atoms. But then, like I said, in the early and late 20th centuries, when brainy scientists came along, they began to modify his theories. So let's modify them. Number 1, he said that atoms are the smallest indivisible particles of matter. Well, he was right, and the scientific community accepted him, but at some point, Ernest Rutherford came along and proved him wrong. How did he do that? Well, he did that by studying the atom some more, and he noticed that the atom can be divided into 3 subparticles. There was the proton. The proton had a positive charge. There was the electron, and the electron had a negative charge. And then there was the neutron, and the neutron had a 0 charge. Okay, 0 charge practically means it has no charge at all. And this was kind of what the structure of an atom was, or Rutherford's own structure of an atom. There were some other chemists that came along and began to put up their own models of atoms, like Niels Bohr, but Ernest Rutherford's model of the atom looked something like this. The proton and the neutron were the nucleus. So let's say this was a proton, and let's say this was a neutron. So the proton and the neutron were like the nucleus of the atom, and then the electron was orbiting around the element. So it would look, this is called Ernest Rutherford's planetary model of an atom. It's something like this. Just imagine the Earth and Mercury and Venus and the other planets orbiting around the sun, and the sun is the nucleus while the electrons are the planets. So this was where I was going to explain what ions mean. Sometimes, or normally in chemistry, an atom can either be positively charged or negatively charged. What does this mean? It means that in science, a positive charge must cancel out a negative charge. So if I have 2 positive charges, there must be 2 negative charges to cancel out the 2 positive charges for that atom to be neutral. But sometimes the positive charges, or the proton, can be more than the negative charges, or the electron, and therefore the atom is positively charged. So let's say I had 3 protons, which I'll call 3p, and I only had 1 electron, which I'll call 1e. This 1 electron would only cancel out 3 protons. So if I have that 1 electron, which is E, and this is P, will only cancel out 1 proton, and we'll be left with 2 protons. It means that the atom is positively charged, because even if 1 electron cancels out 1 proton, there are still 2 other protons, which makes that atom positively charged. So let's do it vice versa. Let's say we had more negative charges than positive charges. Let's say we had 16 negative charges, or 16e, which is the electrons, and we had 14 protons. In this case, only 14 protons will cancel out 14 electrons. The remaining 2 electrons would make that atom negatively charged. In this case, that atom would be called an anion, and in the previous case, that atom would be called a cation. That is what I was talking about, ions. So now you know about the proton, electron, and neutron, which kind of puts off John Dalton's first theory, which states that atoms are indivisible particles of matter. The second theory stated that atoms can neither be created nor destroyed. It means that atoms can't be separated into other atoms, and no 2 atoms can come together to form a new atom. Well, he was correct and still is correct today because in ordinary chemical reactions or ordinary processes, an atom cannot be divided into any smaller unit, or an atom cannot be broken into other elements or other atoms. But when you dive into nuclear fusion and nuclear fission, you're going to find out that you can actually break down an atom into smaller units or break smaller units to form a bigger atom. So here's an example. Uranium-235, which is an isotope of uranium, I'm going to talk about that later, but uranium-235 can go through nuclear fission, which is the separation of its nucleus, the proton and the neutron. Remember, I drew out the planetary model of an atom and I said that the nucleus contains the proton and the neutron. So the nucleus of uranium-235 can be broken down into smaller units and it will release a lot of heat and energy. So it puts off John Dalton's second theory, which states that atoms can neither be created nor destroyed. So when it comes to nuclear fusion, it means the bringing together of smaller atoms to form a bigger atom, and nuclear fission means the separation of a bigger atom into smaller atoms. There's his third theory. His third theory states that atoms of the same elements are alike in every aspect and differ from other elements. Well, he isn't correct in this one, and every chemist will agree with that. Reason why is because of isotopes. Remember, I said I was going to explain that. So an isotope of an atom is practically saying the types of an atom. So an atom can have many types, or isotopes. So here's an example. Chlorine is an atom. Chlorine is an atom, but you can have two types of chlorine. There's chlorine-35, and there's chlorine-37. What is the difference between chlorine-35 and chlorine-37? Because they are the same chlorine, just that one is 35 and one is 37. Well, the difference between the both of them is that this one has more neutrons. This one has less neutrons than this one. Practically, the isotope is gotten from the protons plus the neutrons. So the protons of an atom is what determines the atom. That's one of the things I forgot to explain to you. When you have an atom, if they give you the number of protons the atom has, you can actually determine the element it is. So if I had an atom and that atom has two protons, I would easily know that that atom is a helium element because helium has two protons in its nucleus. So from what I just said, you can determine an element by the number of protons it has. Now chlorine has 17 protons. So if you see an atom with 17 protons, you already know that it's a chlorine atom. So what makes it 35? Well, what makes it 35 is that it has 18 neutrons. So 17 plus 18 is going to give you 35. So in this chlorine atom, you have 18 neutrons and 17 protons. And when they sum up together, you get chlorine 35. But in chlorine 37, you don't have 18 neutrons. You have, can you guess? Can you make a lucky guess? Let's see. You have 20 neutrons. If you add them together, you're going to get chlorine 37, not chlorine 35. So you see the difference? The difference is the number of neutrons. This one has 18 neutrons, and this one has 20 neutrons. There are also some other isotopes. There's isotopes of carbon, there's isotopes of hydrogen, there's isotopes of oxygen. For instance, hydrogen has three isotopes, hydrogen 1, hydrogen 2, and hydrogen 3. Carbon has two isotopes, carbon 14 and carbon 12. So, that is isotopes. And like I said, this puts off John Dalton's theory. The reason why it puts off John Dalton's third theory that talks about atoms being identical, atoms of the same element being identical and differing from other elements, is because when you have an atom that has different isotopes, if the number of neutrons aren't the same in both of the atoms, then the mass of one atom is going to be more than the mass of the other atom. If you had 18 neutrons in one particular atom and 20 neutrons in another atom, the 20 neutrons or the two additional neutrons in that particular atom would weigh more because the neutron has weight, even though it isn't really noticeable with our common units for mass, such as grams and kilograms, but it would have some weight. Alright, so the mass of the element would be different, even though they're the same type of element, but they're isotopes, which means that there's chlorine-35 and chlorine-37. Two different isotopes, but of the same element. So these atoms of an element can differ. So that puts off John Dalton's third theory. John Dalton's fourth theory was put off again. That fourth theory states that atoms can combine, and when they do so, they do in simple ratios, that they combine in simple ratios. And this only holds for inorganic compounds. So by an inorganic compound, I'll give you some examples. In the molecule of water, which is H2O, it contains 2 hydrogen atoms and 1 oxygen atom. So it contains hydrogen and oxygen in 2:1. This is what he means by atoms combining in simple ratios. Here's another example. Hydrochloric acid, which is HCl, is 1 hydrogen atom and 1 chlorine atom, which is 1:1. This is another simple ratio. Here's another simple ratio. Okay, let's see. H2SO4, H2SO4. This contains hydrogen. It has 2 atoms of hydrogen, 1 atom of sulfur, and 4 atoms of oxygen. So this is 2:1:4. Simplified, when you cancel out this 2 and 4, you can get 1:1:2. So these are just simple ratios, and these are inorganic compounds. But when we're combining organic compounds, which are mostly carbon compounds, organic compounds is the study of carbon and the carbon compounds that it forms. So because carbon is one of those elements that can form long chains of carbon atoms, they're going to form thousands and thousands of atoms in just one molecule, and those are not in simple ratios. So John Dalton's fourth theory was put off, in the sense that only inorganic compounds, and only even some inorganic compounds and simple ones, can be combined in simple ratios. The rest and organic compounds will combine in very complex ratios, and they're not going to be simple ratios like John Dalton stated. But the last theory, which says that when we're talking about chemical reactions, it involves the combination or separation of atoms. That is the only theory that holds. Because think about it, whether it's a nuclear fusion, nuclear fission, ordinary chemical reaction, or any oxidation reaction, reducing reaction, any type of reaction at all, redox reactions, they're going to involve the separation or the combination of atoms. So that was the only place that John Dalton was right. Kudos to John Dalton. So now we have listed John Dalton's atomic theory and its modifications. Later we're going to learn about different scientists and different chemists that came along after John Dalton and discovered more things about the atom, including Ernest Rutherford, Robert Millikan, and so many other people, even J.J. Thomson. If you enjoyed this video, please like, subscribe, and share with at least 3 people who you know don't have access to basic education or who is bold enough to explore homeschool, and I'll see you in the next class.